rotational kinetic energy. We saw in an earlier video that the force that we are accustomed with from horizontal motion, when it comes to rotational motion, we have to replace it by the torque. We also saw that the mass must be replaced by moment of inertia. We recall from earlier in the semester that the kinetic energy is 1/2 mv squared, and the work was equal to the change in kinetic energy, or in other words, F multiplied by x was equal to 1/2 mv squared, assuming an initial speed of 0. Based on this analogy, instead of force we can write torque, instead of x we can write theta, instead of mass we can write I, and instead of v we can write omega squared. So this is the work energy theorem for rotational motion, in which the term 1/2 I omega squared is the rotational kinetic energy. 1/2 I omega squared is the rotational kinetic energy. And torque multiplied by angle is equal to the work. But for now, what we did, we just replaced this formula by this. But let's see if this is actually true. So let's say we have a merry-go-round that is rotating, let's say like this, and the reason it's rotating is because I'm applying a force. I'm running with it. I'm running around, right, with a merry-go-round, and I'm continuously applying this force. So this is a merry-go-round, and this is a top view, of course. Right? Well, let's see what happens. The merry-go-round starts from rest, so the initial angular speed is 0. I'm applying a force. This is the radius. So that means I'm applying a torque F multiplied by R. I know that F multiplied by R, the torque, is actually the moment of inertia multiplied by the angular acceleration. Is Newton's second law for rotational motion. F multiplied by R is equal to I alpha. So from here, alpha will be FR divided by I. I'm applying this force for a certain amount of time until the angular speed becomes omega f, but I will simply, actually I can keep it like this, omega f, so the speed, angular speed becomes omega f. Well, I know that if I use my appropriate kinematic equation, I can write the final angular speed in terms of the initial angular speed, angular acceleration, and angle swept. I chose this to be 0 just for simplicity. So this becomes 2 Fri over theta. or 1/2 I omega F squared is equal to F R theta. But Fr is precisely the torque tau. So indeed, what I obtained is that the final kinetic energy is equal to the torque multiplied by theta. So this torque multiplied by theta is the equivalent of work. But again, instead of working with F multiplied by X, I work with the torque multiplied by the angle. And instead of ending up with 1/2 mv squared, I have instead 1/2 I omega squared, because the mass has been replaced by the moment of inertia, the speed has been replaced by angular speed, the same way as the torque has been replaced, is replacing the force, and the angle is replacing the position. So the rotational kinetic energy is 1/2 I omega squared.